So this week we're going to be studying electromagnetic induction. We're going to learn about magnetic flux, electromagnetic induction, and then Faraday's and Lenz's laws. So first of all, we discussed last week, or you guys read last week, about electromagnetism. So essentially, anytime you have a moving magnetic field, it creates an electric field. And anytime you have a moving electric field, it creates a magnetic field. Next week, we're also going to be looking at generators and how we actually produce AC currents based on this entire concept. Okay, so anytime we have a current is a moving electric field. And so that's creating this magnetic field around it. And so we can harness that in order to create electromagnets. And then we can, the other thing we can do is take this magnetic field and move it in order to create a moving electric field, which in turn is a current. So our magnetic flux is very similar to electric flux, except we're using our magnetic field versus our electric field. So magnetic flux is a measure of total magnetic field which passes through a given area. Okay. The difference is that we don't obviously have an isolated north or an isolated south. We always have a north to a south pole. We're always going to have those two in combination. So here is some diagrams. As you notice, this looks very similar to our electric flux, where we have an area and then we have our magnetic field vectors. And we're going to have an angle between that magnetic field as well as the area. A lot of times we're going to look at this right angle here in this second one. And so anytime you have that right angle, obviously that's that 90 degree. So we're not too worried about the angle there. Okay. So it is a change of the magnetic field flux that results in electromotive force or voltage. And it's going to be the sum of that, or the integral of the magnetic field passing through this area. Okay, so essentially what we get is this magnetic flux, which is a symbol of phi, is equivalent to the magnetic field times the area times the cosine of theta. Okay, so the SI unit for magnetic flux is a Weber. Or Weber, I'm not sure, I always say Weber, but it may be Weber, but it's a German physicist and co-inventor of the telegraph. So there you go. And the units is a capital W with a lowercase b, okay? So we've got Webers in flux, we've got a magnetic field in Tesla, we've got an area in meters squared, and then your angle. And once again, anytime we've got that perpendicular angle, there your cosine of 90 is going to be 1, so it's then just your magnetic field times your area. Very similar to electric flux, the actual magnetic flux value itself is not necessarily hugely important, but it's the concept. It's the fact that we can substitute in this equation for a changing flux, that's what we're going to use for the flux itself. Okay? So it will be important to make sure that you are paying attention when you're reading problems, whether they're giving you the flux in Webers or whether they're giving you the magnetic field in Tesla. So here's just another example. Once again, we've covered this in electric flux, that your normal is your area vector. So that's perpendicular to the area, and then the angle is between the magnetic field and that area vector. So here comes Faraday. So Faraday states that the voltage is induced in a circuit whenever relative motion exists between a conductor and a magnetic field. So we have to have some sort of a motion in order for this to happen. Okay? So voltage is induced in a circuit when there's relative motion between a conductor and a magnetic field. The magnitude of the voltage is proportional to the rate of change of the flux. So once again, the voltage is proportional to the rate of change of the flux. So that is essentially the big takeaway for Faraday here. Okay? So what that means is that our induced voltage, or EMF, that electromotive force, is equal to the change in flux over the change in time. So this here is the rate of change of flux. N is the number of coils. We're often just going to be using one loop, whether it's circular or rectangular. As I said, we're mostly going to be using one loop, but in cases of solenoids or different situations, we are going to actually count the number of coils, or it may be given. If the number of coils is not given and it just says a rectangular loop or a loop, then we can assume the number of coils is 1, and that's what we get there. Okay? So this is where, as I mentioned, our flux itself is not as important, but it's not the definition, but the relationship between the magnetic field and area of the loop is how we're going to calculate this. So once again, we can kind of bypass the flux itself and substitute that equation in here. So then we end up with V EMF is equal to the number of coils times the change in magnetic field and area over time. Now, here's the interesting part, is that sometimes it's going to be the magnetic field that could be changing, and sometimes it could be the area that's changing. So we're going to look at both situations in some of our practice examples here. And then just as a side note, this VEMF can also be written like that. So both of those are referring to that electromotive force or the total voltage of the circuit. Also a reminder, and this is going to come up in some of our practice problems, that we always remember Ohm's law, V equals IR. So this is going to come back where if it asks for a current or a resistance, you can actually use this once again if we know the total voltage. Okay, so this negative here, this negative is due to Lenz's law. Okay, so Lenz said, you know what, this has to be negative, otherwise we're going to have perpetual voltage. Okay, so before we get to Lenz, apparently we're doing this one first. So this is our equation here, okay, for one loop. So we're assuming that N is 1, and then we're substituting in BA because we're doing a perpendicular situation here, okay? So your area, remember, is length times width, okay? Or in this case, we just used X. So when you have something that is moving, when your area is changing, you're going to have a length of a rod or a length of it's usually a metal rod that is actually changing that area. And so when we get this here, where your X is over time, if you remember X over time, that actually equals your velocity. Okay, so we can have this equation here that is your magnetic field times the length of the moving rod multiplied by the velocity. Okay, so we're going to also use this equation here in certain situations. Make sure you're adding these to your equation sheet. So here's Lenz. So Lenz says an induced electromotive force generates a current that induces a counter magnetic field that opposes the magnetic field generating the current. Whew. So in English, what that means is you have a magnetic field. Okay, and then if we take something and move it through that magnetic field, we're going to produce a voltage or a current through that. Okay, we're going to produce a voltage, and that voltage and then creates a current. But what does current do? Current creates its own magnetic field. All right, so what happens here is that we have an established magnetic field. Okay, so this is an established magnetic field that we have some object moving in or out of, and it's creating an electromotive force. That electromotive force is what creates that current. Now, this current itself is creating its own magnetic field. So this is a second magnetic field. So what Lenz said is that if this current is creating a magnetic field in the same direction as the existing one, then it's just going to compound it and get bigger and bigger and bigger, and we're just going to end up burning everything up because we're just going to have too much current, because the current creates a magnetic field, the magnetic field creates the current, and so on. So Len said that the induced electromotive force generates a current that is opposite the magnetic field generating the current. So it has to be opposite this already present magnetic field. Okay, so let me clear a little bit of this out. So what we have here, we have to decide whether our flux is increasing or decreasing. Okay, and so in this case, our flux, which is phi, as we're moving this loop into this magnetic field, that means my flux is increasing. If my flux is increasing, then my current has to go in the opposite direction. Okay, so if my magnetic field is up, well, this is a bad situation. This is, I made this one up, but if these are not perpendicular to each other. So let's say this ring is actually on its side. So it's a disc where it's going in this direction, and then our magnetic field is going through it up like that. Okay, so this is where we're going to use our right-hand rule. All right, you're going to point your thumb up, which means that our current in a regular situation should be going counterclockwise. Okay, so that means that current would be going in this direction. However, because our flux is increasing, we have to do the opposite thanks to Lenz's law. So in this situation, because our magnetic flux is increasing, we're going to do the opposite. So I'm going to take my thumb and point it down, and then I'm going to curl my fingers around, and now I know my current is going clockwise. So it's going in this direction. Okay? So if your flux is increasing, then you point your thumb in the opposite direction of the magnetic field. Okay, so we do the opposite. Otherwise, we would get perpetual voltage, which would increase our current, which would increase our magnetic field, and so on and so on and so on. And so that it would be a runaway effect. Okay, and so the opposite is that if our flux is decreasing, then we're just going to do the regular right-hand rule where your thumb is going to point in the same direction as the magnetic field. Okay, so let's go ahead and look at this. All right, so Lenz says that whenever the flux is increasing, the induced magnetic field from the current should oppose the magnetic flux. When it's decreasing, the induced magnetic field should point in the same direction as the flux. So here's two situations. Okay, we have this rod here, okay, is moving in this direction. So we've got two situations. Situation one is my area is increasing, and since my flux is equal to my BA, if my A increases, then that means my flux is increasing. So if my flux is increasing, I have to do the opposite. This X means my magnetic field is going into the page. This is the established magnetic field. So my current has to do the opposite of what my established magnetic field is doing. So instead of pointing my thumb into the page, I'm going to point my thumb out of the page, and then my right hand curls in a clockwise direction. So that's why this current in this situation is going to go in a counterclockwise motion. Okay. Situation number two here, this is moving in this direction. So this area is getting smaller and smaller and smaller. All right, and once again, since my flux is directly proportional to the area, if my area is decreasing, then my flux is also decreasing. So if my flux is decreasing, then I'm going to point my thumb with the established magnetic field, which is into the page. So I'm going to point my thumb into the page, and my fingers curl clockwise around. Okay, so that means that in this part of the loop, my current is going to be going clockwise around that loop. So here's two more examples, and in Canvas I put in some practice examples, so you can just, those are not the optional ones, so you could just practice without having to read more, find different examples. Okay, so this, once again, is an established magnetic field, and it is going into the page. This is the motion of my loop or rectangle. So if it's going into that, then that means my flux is increasing, because right now there's 0 flux, right? And then once it gets in here, it's going to have lots of flux. So it's going from 0 to a lot, therefore I know it's increasing. So if my flux is increasing, I have to do the opposite. So if my magnetic field is going into the page, I'm going to do the opposite and point my thumb out of the page, and my fingers curl around in this direction, which means it is going counterclockwise. For this situation here, my loop is leaving, therefore my magnetic field is getting less and less as it exits, and therefore my flux is decreasing. If my flux is decreasing, I'm going to point my thumb in the magnetic field in the same direction, right? Because if my flux is decreasing, then I could just go in the same direction. So my thumb is going into the page, and once my thumb goes into the page, my fingers wrap around clockwise, so I know this is going to be clockwise in terms of my current, which is going to go around in this direction. Sorry, I'm doing that on the outside. It's going on this box in here, not on the outside. I apologize for that. So let me just get rid of these guys out here. You know what, let me just start over. It's going clockwise around this loop, okay? More practice, I'll go a little bit quicker on this one. So this one is, my flux is decreasing, so I'm going to point my thumb into the page, and on this one, it goes that way, okay? This next one here, it's leaving, so my flux is decreasing, so I'm going to go the same direction. My magnetic field and induced magnetic field are in the same direction, so I point my thumb up. When I point my thumb up, my fingers go in this direction, so that would be counterclockwise. Yellow's a bad color. Here I'm going into a magnetic field, which means I'm starting at 0, and then I'm going to increase my magnetic flux, and so I'm going to do the opposite. So this X is showing into the page, so I'm going to point my thumb out of the page, and then my hand goes counterclockwise. B. This last one here, same thing. I'm starting at 0, and as I go into here, all of a sudden I'm going to have all this flux. So my flux is increasing, so I'm going to do the opposite. This dot means it's coming out of the page, so I'm going to point my thumb into the page, and then my fingers go in this direction, and so therefore it's clockwise. Okay, so on to the fun part of actually putting some numbers with this. First of all, you really need to make sure you understand your units. So when you read a question, you know what it's talking about, and we're not just randomly throwing numbers into equations in the wrong spot. If you need to write out your given information, I highly recommend that. I don't require it, but I recommend it. Okay, so what is the EMF induced when the magnetic field changes from 2.3 Tesla to 0.5 in 10 seconds. Okay, and it gives us a rectangle. So we know we're finding, you can write it here. I'll write out my given information here. So in this case, I have a changing magnetic field, and it's always final minus initial. So 0.5 Tesla minus 2.3 Tesla. Okay. I know my area is, and these are already in meters, so my area is going to be 2/4. And what else do I know? I know some time, which is 10 seconds. Okay, so my EMF equations, I've got two. I've got BLV, but I don't have anything moving. It's not changing that area. It's the magnetic field that's changing. So I'm going to go ahead and use this one here, where this is my flux over time. Okay, and again, instead of flux here, I'm going to have my changing BA, and these are perpendicular, so I don't need to worry about this sine, or the cosine, sorry. So my V EMF, I've got one loop is going to be negative 0.5 minus 2.3 times 2 times 4 for my area over my 10 seconds. And when I throw that all into my calculator, my negatives cancel each other out there, and I end up with 1.44 volts. And there it is. As always, please feel free to pause so you can try these on your own, and then you can, if you get stuck, you can check back, okay? So the magnetic flux through one turn of a 60-turn coil is reduced from 35 Webers to 5 Webers in 8 seconds, which results in an induced current of 360 amps. That's a lot of amps. Maybe not a realistic question. So what is the total resistance? Well, we don't have any equations that we've done recently that has resistance, so that should be a good clue that we're going to find resistance by doing our old Ohm's law. Okay, so first we're going to find the voltage or the induced EMF in order to determine that. Okay, so we're already given the flux in this situation, so but we do have some turns here. So my EMF is going to be negative N times my change in flux over time, which is negative 60 times, I've got 30, whoops. It's always final minus initial, so 5 minus 35 divided by 0.8 seconds. Okay, so when I calculate that all out, I end up with a very high voltage of 2,250 volts. Okay. So now I can go back and find, knowing V equals IR, my resistance is going to be the 2,250 volts divided by 360 amps, and my resistance in this case ends up being 6.25 ohms. All right, I've got 3 more practice problems for you. Again, please try pausing it and try it for yourself, and then replay it or skip ahead to the answers, whatever you want to do. I'm just going to go ahead and work through this one. This one has a diameter, not a radius, and then we're going to need to know our area. So our area of a circle is pi r squared, but it's r, not d. The change in magnetic field is going from 0.5 down to 0. So 0 minus 0.5 is 0, or negative 0.5. Okay, so again, we needed our radius squared instead of our diameter, so we have NBA over time. Calculate that all out, you get 4.42 volts. Okay, this one, yeah, I was gonna say, I'm pretty sure I snipped this from somewhere. It is number 37 in your text. If you want to do some practice problems in your text, if you need more practice, I will make some suggestions. Let me know, because some of them get some pretty weird exceptions to some of the rules, but it's always good practice. Okay, so this one's a little different. An automobile with the radio antenna of 1 meter long travels at 100 kilometers per hour in a location where the Earth's horizontal magnetic field is 5.5 times 10 to the negative 5 Tesla. What is the maximum possible of EMF induced on the antenna? Okay, so we have a length of a rod. We have a velocity that this rod is traveling. Now, this is what I mean by your textbook, and I know Expert TA does this. We do not want kilometers per hour, we need meters per second. So 100 kilometers per hour, if you do the conversion, is 27.8 meters per second. We have a magnetic field of 5.5 times 10 to the negative 5 Tesla. Okay, so anytime you have, like an antenna is a rod, you have something that is a rod or something with a length that is moving, that should kind of be a clue that we're not necessarily doing a moving ring or loop, but we're going to use the other version of our V is EMF, which is BLV. Luckily, we have all of these variables, which is always why it's good to write out your given, because then sometimes your equations should jump out at you. So when we calculate this all out, we get a tiny little voltage, which is good because it's on an antenna. So there you go. Okay, last question, and this one is a multiple part one. Okay, once again from your textbook, number 45. This looks very similar to one of the Expert TA ones. I think the numbers are different, but I'm not sure. Okay, so what we've got going on here, and I'm going to run out of room, so I may switch back and forth. So the rod shown below moves to the right on essentially a zero resistance rail. Okay, so the resistance rail we don't have to worry about. That's like a friction-free surface. We do have this resistor here in this circuit, and we know that this rod here is moving at a speed of 3 meters per second, and we know this established magnetic field is 0.75 Tesla. Okay, and so what does the current circulate, or what is the current and which direction does it circulate? Okay, so first of all, once again, our current we're going to get from our Ohm's law, but we need to first figure out what our velocity or our voltage is. Sorry. So knowing that we've got V, we've got B, and based on our diagram, we know L of this length here is 4 centimeters. Okay, so my EMF is going to be V. Sorry, V. So we've got 0.75, always put the 0 in front of there, times 0.04 centimeters times our 3 meters per second. So I'm getting an induced EMF of 0.09 volts. I can then find my current using my 0.09 volts and my 5.0 ohm resistor, and I know I'm getting a 0.018 amp current. So clockwise or counterclockwise? Well, if it's moving in this direction, this area here is getting bigger, right? So if my area is getting bigger, then that means my flux is getting bigger. So that means I'm going to point my thumb in the opposite direction. So my established magnetic field is going out of the page, so I'm going to point my thumb into the page, and my fingers are wrapping around clockwise, which means that the current is going to be going like this through this loop. So we have a 0.018 amp clockwise current. hopefully that helps with some of these problems. As always, send me questions, and if we need more practice or more practice examples, please feel free to reach out.